let's get started. If you can't get enough of Caddis, there's a competitive programming club in the school. It meets every other week. Competitive programming is about what it sounds like. You have a certain number, a fixed amount of time to solve a certain number of problems. In this case, the problems are on Caddis. And sometimes you work individually, sometimes you work as teams. But first meeting this semester is tonight, or late this afternoon from 4 to 6, and MAB 3159. So if you're interested, you should drop by. We have a team of competitive programmers, 3 that won every year there's the ICPC, the International Collegiate Programming Contest. And this year we had a team of 3 that won the local regional. And as a result, they're going to Atlanta in February for the North American Championship and to Moscow in June for the World Championship. So those kinds of things are on the table when you get good at this. Any questions or problems before we go any further? Not just about that, but about the class. Okay, anybody wants to ask anything? Okay, I want to start by asking you to think about a problem. Suppose that I gave you a whole bunch of strings, like A, B, C, X, Y, Z, and in all I'm going to give you 1,000,000 strings. And some of them may be duplicates and some may not. And I ask you to basically tell me how many of each kind of string there are. Like how many ABCs are there, how many XYZs are there, and so forth. How would you do that? How would you count? Yeah?
I do something similar to what we did with the jumble problem, where you have a set of solution and you go through, and every time that you iterate through the string, and every time you find one that matches, you put it in the set, and then if it's in the set.
Okay, so he's saying essentially start with an empty set, and what you do is throw the string in the set, and then you, well, every time you check to see if the string is in the set. If it is, you know there's one more of that kind. If it's not, you throw it in the set. And when you're all done, you will have counted each kind. What if I constructed the data? We can still think about strings, but I could construct the data so that you couldn't hash it, or you couldn't compare it for a binary search tree. In other words, you couldn't have a fast set. Okay? How would you do it then? Okay, so you got to use a list. Okay.
If there was a way we could pull some information out of it, we could like have separate lists for each something we could get out of the data. So like if we could pull at least like the first letter out.
Okay, but we can go simpler. Let's not worry about decomposing the strings either. Let's just want something really straightforward. Yeah.
Just go down each element of the list and count up how many of each string there is.
Yeah, so basically you start with an empty list, you stick A, B, C in it, and then you stick X, Y, Z, and then D, E, F. And what you have to do every time you insert something new, or maybe we have another list over here that has the count of each one. And then let's say we go to insert D, E, F again. So we would check here, that's not D, E, F. We check here, that's not D, E, F. We check here, that is, and that will become a 2. And we just keep doing that. Okay? So what would the structure of the program look like? How would you describe the very high level structure of a method that did this? Doubly nested loop. Okay? So we have sort of an outer loop iterating through all the strings, that one string at a time. The inner loop would be searching through the list. Okay? Now, let's suppose that there are 1,000,000 strings. How many times does that outer loop run?
Million.
All right, so the outer loop's going to run 1,000,000 times. And what about the inner loop? First time 1, and then 2, and then 3, and then 4, and then so on. So it won't run 1,000,000 times, and on average it'll run about 500,000 times each time. 500 million. Oh, what am I doing? 500,000 times. So whatever code is in the center of the middle is in the body of the inner loop. How many times does it execute?
1,000,000 times 500,000, a lot.
All right. So 1,000,000 times 500,000.
Too many times.
Okay? Now, suppose I wanted you to do this in a reasonable amount of time. How long do you think it would take a computer to do this? We haven't even said what's going on inside of the loop. I mean, there'll be some kind of string comparison and a conditional and increment. Just top of your head, how long would this take to run on a computer, on a laptop?
At least a few seconds.
A few seconds?
It
Few
depends on
minutes?
How long the thing in the middle is taking. If it's taking like a millisecond, then
Okay. So let's
a lot.
calculate.
Not reasonable.
Okay, I'm just going to come here to Google, and I'm going to type, that's what do we decide, 100,000, 1 million.
500,000.
I want to make it so you can see it. Okay, so that was 1 million times 500,000. Okay, that's how many sort of operations has to be done. Where an operation is whatever you're doing in the middle. Okay, so if that's how many operations there are, how many think we can do in a nanosecond? Let's divide this by the number of operations we can think we can do in a nanosecond.
1.
Okay. I mean, how fast is a computer?
Fast. My computer's not that fast.
What's the clock speed of a typical processor?
Like 3 gigahertz?
Maybe 3 gigahertz. That means that would be roughly 3 machine level instructions per second, per nanosecond. So what about this loop? Would saying one loop body, one inner loop body per nanosecond be generous?
Yeah. Probably.
There's got to be more than 3 machine operations to do this. So let's divide that by, I'm going to have to divide by 1. So that's how many nanoseconds it would take. Okay? So that's how many nanoseconds it would take. Let's see how many days that is. No, it didn't work.
Yeah, nanoseconds in days.
Okay, let's do it this way. It worked before class. So we've got that number there. Okay. Let's do it in seconds. Okay. So 500 seconds. Okay. So not like, sometimes you do these problems and you come up with 500 centuries. So this is in the realm of possibility. 500 seconds. Okay. Does anyone, okay, so I'm going to make a couple points. First of all, does anyone know why I brought this up?
To show us that doubly nested for loops are bad?
Well, yeah, doubly nested for loops can be slow,
Just we need to use a good algorithm for the caddis problem this week.
because I want you to use a good algorithm for the caddis problem this week. I am already seeing solutions that are doubly nested loops. Remember, you've got to figure out, there's a bunch of stars, you've got to figure out if, and stars are clustered into galaxies, you've got to figure out whether there is a galaxy that contains more than half the stars. And I tell you, to use a majority vote algorithm, and in particular, do not try to group the stars into galaxies and then see which is the biggest. Because if you try to group the stars into galaxies, the nature of the problem is you won't be able to use any fast set implementations, just the way I've constructed the data, and you end up with a doubly nested loop if you want to sort the stars into galaxies. Okay? What's the maximum, if you look at the Caddis problem, what's the maximum number of stars there can be? A million. So the best you're going to do is, hundreds of seconds. You don't have that long. It just won't work. So believe me, don't try. Just use the majority vote algorithm. The other thing I want to impress upon you is, when you go out in the world, no one is going to expect you to invent an improvement to the Keeretsu algorithm. But people are going to expect you to be able to look at a doubly nested loop and say, yeah, I don't have 500 seconds for this. So this kind of back of the envelope computation, we didn't talk about big O or anything. We just did a few multiplications, little thought, a few multiplications, did a conversion, and found out that, yeah, if this is supposed to be an interactive program, maybe we don't want to do 500 seconds and wait for this thing to run. Maybe I need to see if there's a better way to do it. So you really need to be capable of doing this kind of thing easily, rather than coding up the thing and spending a lot of time doing it and then finding out it's too slow. Okay? Any questions about this? Okay. Let's return to where we were last time. And that was talking about the majority vote algorithm, the first one. Let's go back to this. So that first majority vote algorithm, the one we talked about at the end of class last time, what was the idea behind it? Divide and conquer algorithms usually has some clever idea behind it. What was the idea behind that one? Yeah?
Divide the collection in half, see if each half had a majority or not, and answer based on that.
Okay, so we're given some collection. I'm going to use numbers here. So we're trying to find out whether there is an element that occurs more than half the time. And the idea was to divide in half, solve that problem for the left half, solve the problem for the right half, and then somehow combine those results to solve the problem overall. So if we solve the problem for the left half, are we going to find a majority element? No. So the answer is going to be no in some form. If we solve it for the right half,
Yes.
One.
okay, the answer is yes, and the answer is 1. So the key thing to understand, the key thing for getting the algorithm is that the answers we get here are the only possible answers for up here. In other words, either 1 is a majority element of the big collection, or there is no majority element. So we're doing the recursive call not to solve the problem completely, but to get candidates to check. So you're going to get at most 2 candidates to check. In this case, we just got 1 to check. And you check it just by making a single pass through the array, counting the 1s. And we find out there's more than half, it's 5 and there's 9 elements, so the answer is 1. Now, if we took, if we made 1, 2, 3, 4, 5, 6, 7, 8, 9, so let's say we make this into a 4. We would get the same, right here we get the same answer back, no for the left, 1 for the right. But this time when we count the 1s, there's less than half. So the overall answer would be no. So the only thing that's missing here is you can take me on my word that this works, or you can think about why it works. So can anyone put into words, why does it work that we're basically saying if this thing up here has a majority element, then that thing will have to be the majority element of one of the 2 smaller sets. Yeah.
Well, it has to be more than half, so if it's not a majority element in one of the halves, if it's not a majority element in one of the halves, it has to be in the other half, or vice versa, to be able to actually have enough elements to count.
Okay. So essentially what he's saying is, we got more than half the elements in the big set are ones, let's say. And when we split, they have to be a proportion, some amount between the two. And the fewer you put into one, the more you get in the other. And if you try to evenly balance, there's still going to be a majority. I mean, that's kind of the intuition. It's I'm not going to try to do a formal proof here. Okay? So at the end of class last time, I was taking challenges to see if anyone could construct an example for which this didn't work. I didn't give you much time to try. You want to try now? Yeah.
So it has to be 50% or
No, it has to be over 50%.
over, not
Yeah. If you allow to eat, like this one I have up here now is 50-50. And we could split it so the answer was no, no. If we rearrange things, let's say we put this one over here and put the split right there. The answer would be no because the ones aren't the majority, and no because the ones aren't the majority. Overall answer would be no, but that's the right answer. Right? So that's that algorithm. So let's go back and let's go back to here. Okay, so there's the algorithm. If the length is 0, the answer is no. If the length is 1, return that element. Otherwise, divide into halves and do what we just said. What's the complexity of this algorithm? Now, I expect you to use this algorithm or a faster one for the Galaxy Quest problem, so this probably isn't n squared. We've sort of already made that case. Okay, n log n. So if you're analyzing divide and conquer, you need to just build a recurrence relation. So what is a recurrence relation? The time to deal with n elements. Yeah?
Would it be 2t divided by 2 plus O, well, just 10, I guess?
Okay, so 2t, so 2, because there's 2 recursive calls, 2 halves. So there's the 2. 2t of n over 2, because each subproblem is half the size of the original. So 2t n over 2. Then we got to figure out the overhead. And the overhead is all this stuff. Dividing it into halves. Don't count that. But dividing into halves and then doing this stuff. And the most expensive thing down here is counting. So what's the cost of dividing and basically splitting the array into half? At worst, linear. I mean, it depends. There are tricks you can play. You can use it. We could add extra parameters where you didn't just pass the array, you passed the low and high bound of the region you're interested in. And then no copying would be required. And we could arrange to do the division into halves in constant time, just by not copying. But what's the cost of counting going to be? N. You got at worst got to count twice. So that's n. So that gives us our recurrence relation, 2t n over 2 plus O of n. And then, A is 2, B is 2, D is 1, log base 2 of 2 is 1. So we're in the case where D equals log base 2 of 2. So the answer is O of n to the D log n. And D is 1 in this case, so we got O of n log n. So it's, what would be a faster way to figure out this is n log n, doing a recurrence relation? What I do is look at it and say, oh yeah, that reminds me of an algorithm I've seen before.
It's kind of like merge sort.
It's like merge sort. You look at it and say, yeah, this does what merge sort does. 2 recursive calls, each half, and linear amount of work. That's merge. Linear amount of work is the merge part. So merge sort. So n log n. So this is easily fast enough for Galaxy Quest. Any questions about it? Yeah.
So I understand this is pseudocode, but when you divide them in half over and over again,
How do you know there's no majority?
Isn't there like a possibility that there's, well, no.
There, I mean, yes, you could end up with an array of size 2, but it might contain 2 of the same element. And if it's not, if the initial array is not a power of 2 sides, you can end up with arrays of size 1 or 0. Any other questions? Okay. Here's another one. So here's the idea. Devise a okay, well, you're going to do that. Suppose A has n elements. What we do is we pair them off. And look at each pair. If the elements are different, we kick them out. And if they're the same, we keep one of them. And if there's a leftover element, we're going to have to remember what it was as well. So let me show you what I mean. Let's take this list I had originally. So 1, 2, 3, 5, 1, 1, 1, 4. What we do is just pair them off. That's not right. Let's add another 1 out there. So we're going to, those two are different, so we're going to throw them away. These two are different, so we're going to throw them away. These two are the same, so we keep one. These two are different, so we throw them away, and we have this leftover element that we keep track of. All right, now we recursively solve the problem for the numbers we have left. So we'd be solving the problem for this list right here. Okay, and the answer is going to be either, we're either going to get the majority element back or we're going to get no back. So what do we get back in this case? 1. So the only two elements you have to consider after you get the answer back in the recursive call is whatever the answer, if any, you got from the lower level, plus you got to consider the leftover element. In this case, they're the same. And we take that element, we count how many times it occurs, and we find out it's a majority element. Right? So, believe it or not, this works. Would anyone like to try to challenge it? There's no shame in unsuccessfully challenging it because you know it's not going to work out. But it's a good way to explore, try to understand why it works. Seems too simple to work. Yeah?
How would it work if we had pairs of 1, pairs of 2, pairs of 3, pairs of 4?
So 1, 1, 2, 2, 3, 3, 4, 4?
Yeah.
All right. So basically, these would all cancel out, and not cancel out. We were duplicates, so we get 1, 2, 3, 4. Okay, we make a recursive call. Is there a majority element?
No.
No. So there's no majority element, and there's no odd leftover element to deal with. So our answer is no. Now, what would happen with the 1, 2, 3, 4 when we made the recursive call? They'd both get discarded. We'd have an empty list, and the answer would be no for that. That's where the no would come from. Yeah?
What about 1, 2, 1, 3, 1, 4, 1, 5?
1, 2, 1, 3, 1, 4, 1, 5?
I mean, I know I'm wrong, but I just want
Okay. Yeah, I know you're wrong too. We all know you're wrong. Okay. So what would happen here?
You can come back for no for all of them.
Cancel, 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 cancel.
And then if you had a leftover, then you'd recur to the 1 would just be the majority element.
Right. So this is the recursive call is going to be an empty list. The answer is going to be no. Now, if we had a leftover element, when we got the recursion came back, we'd have to count the 6s. And the answer would still be no. But the point to see is that it's not enough for it to be exactly half. There has to be.
Leftover is a 1.
If the leftover is a 1, what's going to happen?
Trying to count the 1.
When we get the no back, we're still going to look at the leftover. We'll count it, and we'll find out that it is the majority element of that.
Oh, you count it in the original.
Oh yeah, it's part of the original array. It's just not part of the recursion.
So you go back through the entire thing.
Yeah, we go back through the entire thing and count the 1s in this case, and we find out. Yeah.
So the recursion continues until you have this separated.
Yeah. So yeah, you would keep the recursion, the base case is the array is empty.
Why is it faster?
Okay? He asked the question, why is it faster? Well, let's analyze it. Let's do the recurrence relation for this. So, how many recursive calls do we make? Just one. That's why it's faster. Okay? How big is the recurrent? How big is the array each time? It can be empty. We saw that example, right here. You could have 1,000,000 elements in the top level array, and if they pair up just right, you end up making a recursive call with an empty array. So let's look at the worst case. In the worst case, how big can that array be?
Half.
Yeah, can't it be any bigger than half? And linear overhead. And where is the cost of, where does the linear overhead come from?
We have to double check for the extra.
Right, you have to, two reasons. One is doing the pairing operation, and the other is doing the count when you're done. All right, so this one here, what are A, B, and C?
1, 2,
Or rather D.
1,
So A is 1, B is 2, D is 1. Log base B of A,
1.
power to which 2 must be raised to get 1, that's 0. So D is bigger in this case, so it's O of n to the D, or just O of n. So there's a linear time operation. You're not going to get asymptotically faster than that, because you got to at least look at all the elements. Yeah?
Why is it A, B, and D and not A, B, and C?
Couldn't tell you.
It's the person who made this thing.
Yes?
So the validation check where we have to go through and count, that only happens in the specific edge case where the...
No, it happens in both.
Okay.
Let's see if we can, let's construct one where there's not an odd number of elements. Yeah, so like this here, 1, 1, 2, 3. So there's not that leftover element. The recursive call is going to, will carry down the 1 and nothing. So the recursive call is going to be that. We're going to get back 1 as the answer, and we're still going to need to check and find out it's not a majority element. So the whole point of the recursion is just to identify candidates. Okay? Now, here are a couple divide and conquer algorithms, but two famous algorithm designers, Boyer and Moore, years ago discovered a version that wasn't even recursive. And it's based on this recursive algorithm. So let me explain that, just as sort of as a bonus here. So let's take our list here. In this case, let's do 1, 2, 1, 3. Okay, so 6 elements, we have a majority. What you do is you just scan the list from left to right, and the first number becomes your current champion. So 1 is our current champion, and you've seen 1, and you have a count here. So here's our champion, and here's the count. So we see the 1, then we see a 2, and every time you see a 2, the current champion's count is decremented by 1. So in this case, that means that we don't have a champion anymore, because its count goes to 0. So then you go on to the next element right here, and 1 becomes a new champion with a count of 1. We come to the 3, and it cancels out the count and the champion. Then you see the 1, and our current champion is 1. We see another 1, our current champion is 2. And when you're done, the current champion is the candidate. And then you just scan and count how many times that 1 occurs. Think about it, it's based on the idea of consecutive numbers canceling each other out or reinforcing each other. Yeah?
So in this case, if 2 is if you swapped 2 in the first one's place, would the current champion be 2?
So 2, 1, 1, 3, 1, 1?
Yeah.
Okay, so yeah, we start out with a champion of 2 with a count of 1. Then when we got to this guy, the count would go to 0 and we don't have a champion anymore. Then we would see the 1, that would become the new champion, and it's immediately knocked off by the 3, but then we'd have the 2 1s at the end, we end up with 1 as the champion, and we'd count and make sure. Okay? I want to try to foil this one. I find that the further I get into these things, the less people want to believe they work. Yeah.
I want to try to foil it. I just want to ask a question. So,
Yep.
So you're just swapping a champion. So if you don't have a majority element, how does it determine that you don't have a majority element?
Well, you're going to end up, you may end up without a champion.
Oh, okay.
But if you do end up with a champion, you've got to do the pass and count how many times it occurs.
Okay, so it does it can set it to some value that's not a champion. Okay.
Right. Yeah.
If you have like a 1-1-1, there's like 5 elements, and you have 1-1-1, 3-3.
Okay. So we're gonna, when we scan these first 3 numbers, we're gonna end up with our champion being 1, and we've seen it 3 times. Then when we look at this 3, it'll decrement this to 2. When we see this 3, it'll decrement it to 1, and we end up with a champion. Yeah.
So why do we have to, in my mind, if you determine the champion, then it's already the majority. But do you know the case with, because you're saying you have to then go back through and count?
Okay, so why is that last count necessary?
Yeah.
Okay, can someone come with an example? Yeah. 1, 2, 3, 4, 4, 4. So the answer is going to be no here. So 1 becomes a champion and gets knocked off by the 2, and then the 3 becomes the champion and it gets knocked off by the first 4, and then these last 2 4s give us a champion with a count of 2. Or even something as simple as, 3, 2, 1. We're going to end up with 1 as the champion, but there's no majority element. So this is what algorithm researchers do. They take some problem, they find an algorithm for it. I don't know historically what came first, but let's just pretend that the first recursive algorithm, it was n log n, and then the next person comes along and says, I can do better, so they write a paper about how it can be done in linear time. And then someone else says, I don't even need recursion. I can do it just with a single, with a couple loops. And again, odds are none of you will become algorithms researchers, but most of you will be algorithms consumers. So that's the skill you need to hone, is the ability to recognize, oh yeah, this calls for majority vote algorithm, and you may not even remember it, but just look it up. Okay, any last questions about this? Anybody regretting doing Galaxy Quest already? Okay. So this slide here just talks about what we just did. And we just did the recurrence. Okay. That last algorithm, by the way, is also O of n, of course. It just takes 2 passes through to do what it does.
Can we also use that?
Oh yeah, you can use that. Okay. Let's look at another divide and conquer algorithm. So this is the selection problem. You're given an array, linked in, and you want to find the element that would be at index A sub I if A were sorted. And so one thing you could do is sort the array and return A sub I. And that would take n log n time if you use, say, merge sort to do the sort, because almost all the costs will be in the sorting. And you just look up an element. So we want to see if we can do better. So here's an algorithm called quick select that's based on quick sort. So the first method here is just a wrapper. It says return. We call it this helper down here, quick select. We pass the array, we pass the beginning index, the ending index, and the index we're interested in finding. So what it does is, down here, if low is equal to high, the way the algorithm is written, I will also be equal to those three. Low and high and I will all be the same. So we found what we're looking for, and we return a sub I. Otherwise, we partition, using the quicksort partition algorithm. We rearrange the array so that I think I want to just draw this instead of trying to let you read the code there. Have you read the code. I'm doing. All right, let's take an array like this. Two, three, one, 5, 4, 7, 8, 6. Okay, and suppose I gave you an I of 3. What would the answer be? 4. If you sort this, it'll be 1, 2, 3, 4, 5, 6, 7, 8. The 4 will be at index 3, so the answer would be 4. But we want to do it without completely sorting the array, because that would take a long time if the array were big. So what we're going to do is we're going to partition the array using quicksort's partition algorithm. And you remember what it does is we take the last element, at least this is how we're going to do it. We're going to take the last element, and we're going to rearrange the array so that everything that comes before, so that everything smaller than 6 comes first, and then the 6 occurs, and then everything bigger than 6 comes after. And there are various ways to do the partitioning. Sort of a common way is to scan from left to right and from right to left, looking for things that are on the wrong side of the array. So we leave the 6 where it is. So we're going to scan from left to right until we find something bigger than 6. And what are we going to find? Well, we're scanning from the left, so the first thing we'll find is the 7. Then we scan right to left, looking for something smaller than 6. What are we going to find? We find the 4. And this stops when the two indices cross. In this case, they've crossed, which just means that we've got to exchange the pivot element with that element right there, the element we found in the left to right scan. So we end up with 2, 3, 1, 5, 4, 6, 7, 8 as our array. So it just takes a linear scan and rearranges it so the pivot's in the middle. Well, I kind of didn't show the right thing. We would get 8 and 7 the way I wrote the way I described it. So the pivot's in the middle. Everything to the left of the pivot is smaller than 6. Everything to the right is bigger, assuming there are no duplicates. All right, so we've done the pivot. We've rearranged it. Now we're looking for the thing that would be at index I if the array were only sorted. How can we use the fact that we have partitioned the array to help us here? First of all, what would quicksort do at this point? Yeah, so it would divide the subarray to the left of 6. It would sort it in place, and it would sort the 8, 7 in place, and you'd be left with a sorted array. It would make 2 recursive calls to sort the 2 chunks. The 6 would just stay where it is, because it's in the right spot. So the one thing you know about this array is the pivot is in the right index. So we want to arrange so we don't have to search both halves. We just want to search one half. Got an idea?
Did you choose the pivot?
Well, the pivot's already chosen. Oh, how do we choose it?
Yes.
I just took the last element. But there are all kinds of ways to partition the array. It doesn't really matter. Yeah.
So you get the index of the pivot and you see whether it's greater than or less than.
Right. Look at the index of the pivot, because the pivot you know is in the right spot. So let's see, 0, 1, 2, 3, 4, 5, index 5. So there are 3 possibilities. If the index of the pivot, let's call it J, we'll call it P. If P is equal to I, what do? You found the thing you're looking for. We know that 6 is in the right spot. So if we happen to be looking for the element at index 5 of the sorted array, we could just return 6 at this point and be done with it. We got lucky. Okay? What if the pivot is greater than the index we're looking for?
We can ignore the right.
Well, no, so let's say the pivot is 5. Suppose we're looking for index, we're thinking index 2. Right, we would ignore that subarray because we know nothing. The indexes over here are all bigger than 5. So we're going to look in the left subarray. And what if the pivot is less than the index we're looking for? Then we ignore the left and look on the right. So let's say we're looking through the thing that would be at index 1. So we would recursively search this array, 2, 3, 1, 5, 4. Okay? We would do the partition, which would leave us as this situation, 2, 3, 1, 4, 5, where this is the pivot. And what would we do? That's at index 3. So what would we do next? And we're looking for I equals 1.
Ignore everything to the right.
Ignore the stuff to the right and pay attention to that right there. So we're down to 2, 3, 1. And I'll stop there. You can see where we're headed. We just keep doing it. Well, maybe it's worth bottoming out once. So 2, 3, 1. We pivot. What will the array look like after we...
1, 2, 3.
well, actually, it will be... the 1 will definitely be on the left, but it'll be like that. 1, 3, 2. We look at this. Oh, no, sorry. This was our pivot. It's at index 0, so what subarray do we look at now?
To the right.
Just that 3, 2. And, continue. Well, I think I'm getting to the point of diminishing returns. One thing I should note is I've been lucky that I'm always looking to the left. Let me back up and show you why. Let's go with this one right here. Suppose we'd been looking for the thing at index 7. In other words, the 8. What would have happened the way I'm drawing the array here? We would look to the right of the pivot, which is at index 5, and I've been copying the array out, 8, 7. That thing, if we're looking for the thing at index 7, that only has indexes 0 or 1. So the way the algorithm really works is when you make the recursive call, you don't actually copy the elements out. You keep the same array with the same indexes, but you just focus on that chunk. So the indexes stay the same. Once you start copying things out, the indexes start changing and it all gets screwed up. Okay? But since I was always going to the left, it didn't come back to bite me until I got toward the end. So that's quick select. And the question is, well, first of all, any questions about how it works? It's just a partition. It's sort of a combination of the partition algorithm from quicksort and a binary search. You partition, look at the pivot's index, and then you do one of 3 things depending on where that pivot is. Well, let's look at the analysis of this. So there's the algorithm right there. You can see I have A, low, high, I. So it's happening in place, just like quicksort happens in place. If low and high are the same, we have converged to an answer, just like binary search converges to an answer. Otherwise, we do the partition, and then we got these 3 cases. One is a base case, we return immediately. The other 2 are calls to quick select that either look at the left or the right part. So here's a less detailed depiction of what's going on. So we're quick selecting A of 4. I just did the partitioning. 8 was the pivot. So, I think 4 was the pivot. So we throw that away, 8, 5, 7, 6, and search in that. We do another partitioning and throw away half, and all we're left with is what's at index 4. I think what I did on the other slide is more illustrative. Let's do an analysis. What's the best case? What's the best case for quick select? Yeah?
Pick the right pivot on the first go.
Right. It turns out that the pivot is at the index that we need. So what would be the complexity of this? It would not be constant, right? Because before you get to the looking at the pivot, you got to do that partition. Yeah? O of n, because you got the partition is O of n. What about the worst case? Assuming that your partition always magically splits the array exactly in half, which isn't necessarily the case, but let's pretend that that is. Yeah. Okay, n log n. Let's that's the complexity of quick sort when you have a perfect partition each time. Hopefully we do better. Why should we expect to do better than quick sort? Yeah?
At that point, just sort it.
Yeah. If that's going to be, well, we do have this nice best case. But the other way is you're only making one recursive call. Surely just making one recursive call ought to be better. So there's our, let's see, that's the recurrence. So making one recursive call, half the size of the original, plus a linear amount of work. And that turns out to be O of n. So sort of on average, quick select is O of n. Now, what would be the recurrence if we always got the absolute worst? So you had the pivot and then everything was to its right, or vice versa. Pivot and everything is to the left. What would T of n be equal to? Yeah, it's going to be n squared, but I'm going to see what the recurrence looks like.
T of n minus 1.
Right, T of n is equal to the cost of dealing with n elements is going to be whatever the cost of dealing with n minus 1 elements is, plus the cost of that partition that didn't work out very well. Now, what does the master theorem have to say about this? What are A, B, and D? Now, you could say A is 1. There's one recursive call. And you can say D is 1. But what's B?
Still divided by 1.
It's not in the right form. It's not in the form that we could do. It has to be T times some fraction. I mean, N times some fraction. N times 1/2 or N times 2/3. Not N minus 1. So the master theorem doesn't apply to this. But we know what this is. This is just doubly nested loop deal. You know, the first pass takes n, the next pass takes n minus 1, the next pass takes n minus 2. That's n squared. So the we won't prove it, but it's possible to prove using probabilistic arguments that the average case is O of n. You sort of got that idea up here, but you can actually show that on average it takes O of n. There is an algorithm that you can find out there that is guaranteed to work in linear time. It works by making 5 recursive calls at each level. So it works to split the array into 5 chunks and then makes 5 recursive calls. And, I think in practice it would be slower than quick select until you got very large arrays, but it is linear worst case algorithm. Okay, let's take a break.
How are you comparing I with
All right, let's get started again. All right, so I'm sure you haven't forgotten Keeretsu multiplication yet, but this is just this was the algorithm, and the key idea was that we could multiply two n-bit numbers recursively by splitting them in half and making 3 recursive calls, as opposed to 4 is what we originally thought. But by making 3 recursive calls, it works out to be faster than n squared, roughly into the 1.59, or precisely into the log base 2 of 3. What I want to do now is see how well this works out in practice. Now, suppose we do grade school multiplication. So remember, the way it's going to work is we're going to represent our long integers with blocks of 32 bits. And then we'll just do grade school multiplication like normal, except we're dealing with, instead of multiplying 2 base 10 digits, we'll multiply 2 32-bit blocks using machine machine arithmetic. So each of those pairs of blocks will be multiplied in constant time. Of course, we'll have an array of these things. So I computed the average time it took to multiply pairs of n-bit integers for various powers of 2. For n equals 1 up to n up goes to 2 to the 17. So remember, 2 to the 20th would be about 1 million. So we're not up to 1 million bits, but a lot. It's fairly large. So what would you expect that plot to look like? Besides starting low and ending high, what would happen in the middle? What would the shape of it look like? How long would it take to multiply 1-bit numbers? Be pretty fast. What about multiplying a pair of 2-bit numbers? Same. The computer doesn't care whether a 1-bit number just means that first 31 bits are 0 and then there's 1 bit. What about 4-bit numbers? Same. 8, 16, 32? That's all going to be the same. Okay? Then what about 64? That going to take longer? Mm-hmm. Yeah. How many 32-bit multiplications do we do there? You got the first number is 2 chunks of 32 bits. The next number is 2 chunks of 32 bits. So you got to do 1, 2, 3, 4 machine multiplications using grade school algorithm. So the curve is going to be flat up to 32 bits. And then how's it going to grow afterwards? What would you describe? Quadratic, because it's an n-squared algorithm. So it's going to be flat. It's not going to start growing until the numbers start growing beyond 32 bits. So there it is. Can't explain that slight dip around 5, but it's some artifact of my timing. But you can see that it's flat and then it starts growing. Now, that doesn't look like a quadratic to me because it's, you expect it to steepen, but it's a straight line. But look at the axes and tell me why it's a straight line. Yeah.
Is a logarithmic scale?
Yeah, in fact, it's double log. Log, log. This is log of n. This is log of the amount of time. And on such a plot, the slope of the line corresponds to doubling behavior. So we know that when you double the size of the input, it quadruples the running time. So on this plot, this line has a slope of 4. And you can sort of see that if you figure it out. Let's see, you go 2 units here. So to get from here to here, you're doing 2 units. And up here, you're growing by 8 units. No, okay. Anyway, take my word for it. I'm not going to be able to justify it, but no, I'm okay. I take that back. It isn't the doubling behavior; it's the slope. It's the exponent, the 2. Slope is 2. You go over 2 units while you're climbing 4. Slope is 2. So that's the exponent for n squared. So you get that straight line. So the end of the third would have a slope of 3, be a steeper line. Okay, glad I straightened myself out. Okay, there's the table. And you can see that the ratio settled down after a while to a ratio of roughly 4. This is what we expect in the doubling behavior. Now, let's do Keeretsu multiplication. Again, same pairs of n-bit integers. We're going to superimpose the plot of Keeretsu on here. How do you expect it will look? Yeah?
At first it'll be slower, but then as time goes on it'll catch up.
Okay. All right. Slower than catch up, yeah?
Half as steep.
Half as steep? Well, the slope of this one was 2 because of n squared. The slope of the other is going to be what? Log base 2 of 3. So that's like 1.59. So it's not half as steep, but it's going to be less steep. Is it going to have this flat area at the beginning? No, because Keeretsu would just keep splitting until it gets down to single bits. So it's not going to have any period where it doesn't matter and then it starts growing. So this is what it looks like. Surely it's not taking any of your time, but anyway, once you get going with at least 2 bits, it's flat. Now, think about that. It's less steep, right? They'll intersect eventually, at which point, for that problem size, Keeretsu will be faster. So pure Keeretsu is not faster than grade school for 2 to the 17 bits. In fact, the difference is like, what is the time, we've got the log of the thing, so this is, many, many times slower than Keeretsu. And where are they going to intersect? You think they'll intersect before they get to the courtyard on the other side of that wall? Or will it intersect before it gets to the wall over there? I'm not sure they're closing fast enough. And how big will n be at that point? It's more than 2 to the billion, 2 to the trillion, whatever. It's going to be incredibly massive. So Keeretsu looks like completely useless in practice. That's pure Keeretsu is completely useless in practice. So we got to do something to resuscitate Keeretsu. Yeah, what's the fundamental problem?
Breaking it down to 1 bit.
Breaking it all the way down to 1 bit. If we were smart about it, maybe we could, once we recurse down and got to 32 bits in each number, we could just do grade school right then. And it would eliminate this initial jump, followed by that grow. So if we could sort of limit the initial grow, maybe we could pull it down here somewhere, and it wouldn't be so handicapped at the beginning. All right, so what do you expect the ratio to be? So we saw the ratio here was 4 between successive things. What's the ratio going to be between, what do we expect it to converge to in successive rows here? And the way you do that is you just say, okay, if you want to know what's the ratio, what's the ratio between the running time for double size to the ratio for single size, you just compute it. We take, the formula is n to the log base 2 of 3, so we compute 2n to the log base 2 of 3, and we compute n to the log base 2 of 3 and divide them. That's the ratio between successive doublings. And if you do that, you get 2 to the log base 2 of 3. And what is that?
I don't know.
Yeah? May not know, but I'll tell you. Yeah, it turns out to be 3. So that's nice. And you can see that it settles out pretty quickly in tripling operation.
Ooh, wow.
Okay, and that's easy to do because we're taking 2 to the log base 2 of 3. They're inverse operations, so the answer is just 3.
It's a nice first case, though.
Yeah, I don't know. Yeah, at the beginning, I don't know what's going on there. Okay. So it's clearly faster asymptotically, but in practice, it's pure Keeretsu has a suspect design decision behind it. Okay, so what we're going to look at now is a blended algorithm. This is a common thing with divide and conquer algorithms. You have a non-recursive algorithm that is asymptotically slower than the recursive algorithm, but is actually faster for small inputs. So what you do is you take the divide and conquer algorithm, you let it run, and it gradually divides things in half. But instead of going all the way to the base case, at some point you say enough, and you solve the individual problems you're generating with the non-recursive algorithm. And that works nicely because divide and conquer algorithms operate by producing smaller versions of the original problem. And when they get small enough, you just solve the problem the old-fashioned way and hope that the combined algorithm is faster than either of the original ones. So here's our algorithm. We're going to pick some threshold. And when x and y are both less, when their bit length are both less than the threshold, we're just going to grade school multiply them. Otherwise, we're going to do a Keeretsu-like thing by splitting into the halves, doing the three blended multiplies, and recomposing. I want you to notice that this here is not Keeretsu. What makes this not Keeretsu? This piece of code right here. It's kind of a trick question. Yeah.
Is it because it's calling itself blended multiply and not Keeretsu?
Right, because it's not calling Keeretsu, it's calling blended multiply. Right? Right? I'm saying this because it's going to be the answer to a question you're going to ask in a few minutes. Okay? However, I've got to tell you, this is a very common programming mistake I make. Is when I take an algorithm and decide to make a blended algorithm, I'm always forgetting. So I start with Keeretsu and then turn it to blended multiply. I put an else around the old Keeretsu body. I stick a different if up here, and then I forget to change this to blended multiply. I leave in a call to Keeretsu. And then it doesn't help at all what I'm doing. So that's a gotcha. That's on my list of things that I always check for when I start having problems programming. All right, so there's our blended algorithm, blended multiply. We're going to play the same game we did with it. The question becomes, what should the threshold be? So what do you think? At what point should we switch from this divide and conquer thing that's cutting up the numbers and go into the base case and just multiply the numbers already? How many bits? 32 seem reasonable? Seems like something to try. Well, let's see what happens here. I'm sort of assuming here that x and y are the same length. If they're very different lengths, you're going to end up, let's say x is a lot longer than y, you're going to chop y up pretty finely before x gets small enough. So we need to think harder about this, but we'll just assume right now x and y have the same number of bits. Have you seen this type of idea before? I expect you have. Blending a divide and conquer algorithm with a non-recursive algorithm to get something faster than either of the originals. Where'd you see it? Yeah. Okay, so like combining merge sort with insertion sort. So, yeah. And I've already mentioned why it's important to, for the top level algorithm to be recursive divide and conquer, because it generates the smaller problems for us to solve the other way. So there's our plot. What do you think it's going to look like when we merge, when we show the new algorithm, the blended algorithm, using a threshold of 32 bits? Yeah?
It's going to look like the grade school, but it'll be flat, and then the slope will be just plus.
All right, so it's going to follow grade school exactly because it is grade school for these small bit numbers. except there's that additional if, but that's small. It's going to get out here, and then it's going to change. And what we would like to see is that when it switches over, when it gets bigger than this, it's going to, it's going to stay below the blue, with the lower slope. That's what it does. So just as we expected, it follows this blue line. It gets up to 64 bits, only slightly worse. And then it does this jump. And then you can see it's converging. It's going to cross the blue line soon, but still it's going to be a massive number before it crosses. What's going on here? Yeah?
Is the threshold set too low?
Turns out the threshold is set too low. Our intuition about the optimal place to set the threshold was wrong. 32 bits is too low. You're better off switching over to grade school sooner. Here's one way to think about it. You start with a big old number, or talk about sorting. You start by doing merge sort in a big array. You make a pair of recursive calls, you've got 2 arrays. Then at the next level, you got 4 arrays, and then 8, and then 16, then 32. So if you look at the recursion tree, say the array starts out with 1,000,000 elements, and the number of individual problems on each level of recursion is doubling at each level. How many are you going to have at the bottom? How many base cases do you hit? A million, roughly. You end up with a bunch of 1-element arrays. So if you look at a recursion tree, the top levels have relatively few nodes. All the actions at the bottom of the tree. Half of the nodes in a binary tree, in a balanced binary tree, are at the bottom level. So if you cut off the bottom level, you've gotten rid of a tremendous amount of stuff. If you cut off the bottom 2 levels, you've gotten rid of 3/4 of the stuff in the tree, and so on. So every time you raise that threshold a little bit, you're eliminating a lot of overhead, a lot of methods that get created, a lot of method calls that get created, and stack frames that get pushed and popped. So clearly you can't set the threshold all the way at the top, or you're just left with the original inefficient algorithm. And all the way at the bottom is bad. Somewhere in the middle is needed. So how do you determine? I'll tell you what no one has suggested. People always suggest, well, maybe we should figure out where the green and the red cross and set that as a threshold. Does that make sense?
Yeah, but it feels like it won't work.
That would be a sad conclusion if the threshold occurred when the green and the red crossed. Because they effectively never cross, at least for the size of numbers we're talking about. And the thing to remember is that is, if we were choosing, will I use pure Keeretsu or will I use pure grade school? Yeah, you would use pure grade school until those lines crossed. But we're not comparing pure Keeretsu to pure grade school. We're comparing the blended algorithm, which is different from either one. So how would you decide the right threshold?
Trial and error.
Trial and error. Just do some experiments. Set the threshold at different values, time it out, and see what works out best. So let's see. Before we do that, we'll call this blended 64. Oh, I see. So if it'll let me go back. No, it doesn't. The reason it tracked to 64 is I actually set the threshold to 64 in that graph we just saw. It would have been even worse. Okay. What would you expect when I show you the table for blended 64, what do you expect the ratio to look like? Will it be 4? Will it be 3? Will it be somewhere in between? Will it be better than 3? Yeah?
It'll be 1, and then there'll be like one big ratio, and then it'll be 3.
It'll eventually settle down to 3, because in the end, we're basically doing Keeretsu as the n gets bigger. And this is really weird anomaly right here, 32. But that's right around, or that's where it jumped. That's where we're doing the, yep. So we saw that. So what I did was I took pairs of 10,000 bit numbers. I used thresholds ranging from 512 to 2048 and steps of 256, and just timed how long it took to multiply with different thresholds. And that's what I saw. So if the threshold was too small, so this is just 512, so the 64 is really bad. Then it sort of bottomed out as the same, and it picks off again. And this wasn't a very precise analysis. I was always using exactly 10,000 bit numbers. Yeah?
So would a good choice for the point to like start at be maybe where the algorithm's ratios are kind of similar? Or
So
is
look
there
where the
a rule
ratios
for
are
that,
similar?
I guess? Like
Yeah, I've never thought about that. I don't know how to, I mean, you can come up with the exact formulas for the performance of the two algorithms, you can sort of solve for it. But you have to know the constants. So I think you really gotta, I think it really just takes experimentation. And you wanna do a better experiment than I did with different length numbers. I once looked at the Free Software Foundation's big integer package, which is written in C, and they use 4 different algorithms. They blend 4 different algorithms. So they have grade school, and then they have Keeretsu, and then they have 2 more on top of Keeretsu that use fast Fourier transforms. So if the number's long enough, it switches from the one recursion to the next recursive algorithm to Keeretsu and finally to grade school. And the thresholds are dependent on what kind of machine it's running on. So if you program in C, you can say, if I'm running on such and such a processor, do this. And so there are all these if-defs in the code setting the thresholds differently for different kinds of machines. So it pales in comparison. They did a lot of experiments. I just did one. So really anything in here, I guess right here is going to work out okay. So let's see what I picked. So I picked 1280. So that's the plot as it currently is, the 64-bit threshold, blended 64. What do you at least hope it's going to look like when we use a threshold of 1280? Hopefully it'll track along the blue and eventually stay below it. But we don't want to see it above. So this is what you get. So we get it tracking, and then it gradually starts to pull away. So the place where you can see that it's really pulling away is sort of right about here, which is 2 to the 11th bits, which is about 2,000 bits. Divide that by 3, we're talking 2,000 divided by 3, 700 digits, something like that. That was, and of course that threshold is just for my implementation. We could tune it and try to make it better. But that starts to look reasonable because when you do encryption, you are dealing with hundreds of digits, and you're doing lots of multiplications. And the table, again, it converges to 3 because in the end it's going to perform like Keeretsu. The base case is different, basically.
It's not 7,000.
And you don't see that big jump. Okay? So this is, like I said, very common that it's not always this extreme, but for small arrays, insertion sort does better than merge sort, so it can be advantageous to blend them. Okay. Any final questions I can answer about this? Okay, I'll see you next time.